Today we're going to be talking about limits at infinity. If as x approaches a number, let's say c, from the left and y gets infinitely large, we'll say that the left-hand limit of f of x equals infinity. This is a bit of abusive notation because if the function does get infinitely large, technically the limit doesn't exist. But it is still useful to know what the behavior is. So we'll say the limit equals infinity if the function gets infinitely large as x approaches a value. Similarly, if x approaches that same value from the right and the function gets infinitely large, then we'll say the right-hand limit equals infinity. And as always, if the left and right-hand limits equal each other, then that's the overall limit. We can do the same thing for minus infinity. So if the function instead gets infinitely small as we approach that value, that limit we'll say equals minus infinity. The place at which we go to infinity or minus infinity is called a vertical asymptote. So if you hear people asking you about vertical asymptotes, it just means at that x value, our function gets infinitely large or infinitely small. So if we take a look at this graph for 1 over x plus 1, we can look at this line right here. This is a vertical asymptote because as our x gets closer and closer to minus 1, we're going to infinity and minus infinity. In particular, if we look at x approaching minus 1 from the right-hand side of this function, then we're getting bigger and bigger and bigger and bigger and bigger. So this right-hand side is infinity. And as we approach from the left-hand side, we're getting smaller and smaller and smaller and smaller and smaller. So the left-hand limit is minus infinity. In this case, the left and right-hand limit don't match. So we can't say the limit itself is infinity, but we can say there's a vertical asymptote at that point. Now, if we didn't have the graph, it's pretty clear from the graph what's going on, but if we didn't have the graph, if we just had this function, what we would do is we would plug in numbers that are closer and closer to minus 1. So for instance, if we wanted to plug in, let's say, minus 0.9, we would get 1 over minus 0.9 plus 1 equals 1 over 0.1. And this is a positive number, you'll notice. And as we get closer and closer to minus 1 from the right, that number is going to stay positive. So that's where we're getting our infinity from. If we actually plug this into the calculator, this will be a really, really big number. Similarly, if we come in from the left, we'll plug in, let's say, minus 1.1 plus 1. And this also gives us a really big number, but this time it's negative, which is why we're going towards negative infinity. As we're looking at fractions, we can kind of tell what's going on because whatever is happening on the bottom of the fraction is the opposite of what the fraction as a whole is doing. So for instance, if I have the bottom of the fraction getting really, really, really big, the fraction as a whole is getting small. And this is maybe not surprising, right? If I plug in, let's say 1 over 10, that's 0.1, that's a pretty small number. If I say 1 over 100, that's even smaller. If I say 1 over 1,000, that's even smaller. So as the bottom is getting bigger and bigger and bigger, the fraction as a whole is getting closer and closer to 0. Similarly, the opposite is true. So if the bottom of the fraction gets very, very small, as we saw in our example here, then the fraction as a whole gets very large. So as we're plugging in smaller and smaller numbers on the bottom, the fraction is going towards infinity. So because of this convenient rule of thumb, we can find the vertical asymptotes of a fractional function by finding the places where the bottom of the fraction is 0 and the top isn't, right? So if I can find the place where the bottom of the fraction is 0, that means around that point, the bottom of my fraction is getting very, very, very small. So the fraction as a whole is getting very, very, very big. So if we want to find the vertical asymptotes of this fraction, we want to figure out where the bottom of this fraction, this x squared plus 3x plus 2, is getting closer and closer to 0. So we'll say, where is it true that x squared plus 3x plus 2 equals 0? Well, we can factor this into, let's say, x plus 2 times x plus 1 equals to 0. That means if I have two numbers multiplied equaling to 0, one of them has to equal 0. So we either have x plus 2 equals 0, or we have x plus 1 equals 0. And if x plus 2 equals 0, that means x equals minus 2. And if x plus 1 equals 0, that means x equals minus 1. And you'll notice that if we actually plug that value in to the top, we're not getting 0 on the top. So we've got a non-zero number over 0. So these are the two places where we have vertical asymptotes. So again, all we've done is we said, where's the bottom of that fraction equaling to 0? When the bottom of that fraction equals 0, my fraction as a whole is exploding either towards infinity or minus infinity. Those are going to be my vertical asymptotes. Now you'll notice when we're talking about this, we had to clarify that the top of the fraction is not 0, right? If the bottom of the fraction is 0 and the top isn't 0, then that's where we have our vertical asymptotes. Why did we have to do that? Well, that's because if we have 0 over 0, this is an indeterminate. This is an expression that doesn't mean anything. And the 0 over the 0, that's what we've been seeing for the last couple of weeks as we've been evaluating functions. And when we got 0 over 0, we had to try something new, right? Usually it was factoring or simplifying in some way. Why do we not know what 0 over 0 equals? Well, we just said as the bottom of our fraction goes to 0, the fraction as a whole goes to infinity. But another rule of thumb is that if I have 0 over anything, that should be 0. So which one wins out? Are we going towards 0 or are we going towards infinity? We don't know. That depends on the rate at which the top and the bottom go towards their zeros. We can't tell. So this could be 0, this could be infinity, or it could be a number in between. Similarly, if I have infinity minus infinity, which one of those infinities is bigger? I don't know. Is this 0? Is this 5? You don't know because you don't know how big those infinities are. Similarly, infinity times 0, rule of thumb, infinity times anything should be infinity. Separate rule of thumb, 0 times anything should be 0. So which one of those wins out? And we have the same kind of thing with all of these standard indeterminate forms, right? So if the bottom of a fraction is really large, the fraction as a whole gets really small. That's what we were just talking about. So this infinity tells us we should be going towards 0, but this infinity tells us we should be going to infinity. Which do we do? So these are indeterminate forms. We can't tell anything if we have an indeterminate form. However, if we don't have an indeterminate form, that's when we can find our vertical asymptotes. So vertical asymptotes are places where the function goes to infinity or minus infinity. Now, we can also have horizontal asymptotes. We're just looking at where does the function go to infinity, but we can also ask where does x, what happens when x goes to infinity? So if we take the limit as x goes to infinity, and that limit actually equals a number, then that is a horizontal asymptote. So what I mean by this is as x gets bigger and bigger and bigger and bigger, does the function approach just a single value? Or as x gets smaller and smaller and smaller and smaller, does the function approach a specific value? These would be our horizontal asymptotes. If we look back at our function 1 over x plus 1, our horizontal asymptote is 0 in both directions, right? As x is getting infinitely large, we're getting closer and closer and closer to 0. And as x is getting infinitely small, we're also getting closer and closer and closer to 0. So this would be the limit as x goes to infinity of our function f of x equals 0. And similarly, the limit as x goes to minus infinity of f of x also equals 0. And we can see this by exactly what we were just talking about. As the bottom of the fraction gets very large, the fraction as a whole gets very small. So if I plug in infinity down here, I've got 1 over infinity, right? So think of that as like 1 over a billion. If you plug that into your calculator, you get something infinitesimally small. We're getting really, really, really close to 0. And similarly on the other side. So this, this line, y equals 0, is my, y equals 0 is going to be my horizontal asymptote. All right, so can we shorthand this at all? Can we do a shortcut to find our horizontal asymptotes? Yes, we can, especially when our function is looking like a polynomial over a polynomial. Okay, if our function is looking like a polynomial over a polynomial, then we just have to look at the leading terms of the polynomials to tell what's going on. So let's do this as an example, and then we can go back and look at the rule of thumb. So if we're looking at this example, we have this function f of x, and we've got x squared plus 2 on the top and x cubed minus 3x plus 9 on the bottom. Now, if I'm looking at the limit as x goes to infinity, this looks like it should be infinity over infinity, which is an indeterminate, right? But what's happening? The bottom is growing much, much faster than the top, right? As we plug in bigger and bigger and bigger and bigger numbers, the bottom is going to get huge much, much faster than the top is, right? What that means is we don't actually have infinity over infinity. What we actually have is something much, much smaller over something much, much bigger. What this means is this limit is going to 0, right? So the limit as x goes to infinity of f of x, this is going to equal to 0, because more or less what we have is we have something huge over something not as huge, right? Now, if we look at g of x, we have it the other way around. Again, naively, this would look like infinity over infinity, but in reality, what's happening is the top is getting really, 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 really big, much, much faster than the bottom is, right? So think of this as like a billion over 1,000. Yeah, 1,000 is big, but compared to a billion, it's barely anything. So we can think of this as like infinity over a number. And so as we're looking at the limit as x goes to infinity of g of x, this thing is going to be infinity. Now, our last one is a little bit tricky, but follows the same rule of thumb. Again, if we plug infinity into here, naively, this looks like infinity over infinity. But let's think about what's actually happening here. This x cubed on the top is growing much faster than 7. 7 is just staying 7, right? So in comparison to 7, 2x cubed is getting gigantic. So the 7 basically doesn't matter, right? Similarly, x cubed is growing much, much faster than x, right? So again, this is like a billion plus 1,000. 1,000 sounds really big, but if you're a billionaire, an extra $1,000 doesn't really matter, right? So this is more or less, as we're getting bigger and bigger and bigger, going to look like 2x cubed over 3x cubed. The rest of the terms don't really matter. Now we can cancel our x cubes and we're left with 2/3. So the limit as x goes to infinity of h of x is going to equal to 2/3. This is always true. If we look at our leading terms in our polynomial fraction, if the terms are the same, then our limit is going to be the ratio of the coefficients. So here that ratio is 2/3. If we have that the bottom is bigger than the top, right? That was this first one, the bottom's bigger than the top, then the limit is going to be 0. And if we have the top bigger than the bottom, that's what happened in our second one, the top was bigger than the bottom, then the limit is infinity. So to recap, we can look at limits with infinity if we're looking at x approaching a number and the function itself gets infinitely huge, that's a vertical asymptote. If we're looking at the limits as x goes to infinity and we're actually getting a value, that's a horizontal asymptote. And we can evaluate these limits at infinity of polynomials pretty easily by looking at whether the top or the bottom grows faster.